So today we're going to continue our discussion of marine sediments, and then hopefully at the end of the lecture, roughly the last half, we'll start talking about seawater. Mostly today we'll be talking about physical properties of seawater, and then on Monday, hopefully we'll get to the chemical properties of seawater, in particular things dissolved in seawater and its ability to dissolve things. At the end of lecture on Wednesday, I had started we were talking about the various genetic classifications of sediments, classifying sediments according to how they're formed or what mechanism causes them to be deposited. And so we are looking at a particular example of cosmogenic sediments, the impact of a large, probably asteroid-type object into the Yucatan Peninsula in Mexico, which is observed to correlate with the mass extinction, the loss of the dinosaurs and many marine organisms, and also shows up in the sedimentary record as these funny deposits of coarse-grained materials in many places, particularly relatively close to where the impact occurred. So here's a more detailed picture. This is the last slide I showed on Wednesday. The impact crater as mapped out by geophysical data by looking at magnetic anomalies or gravity anomalies, or actually this is an area that's been explored for oil, so there are actually drill holes. And so we have a sense of where the crater is. It's buried today, but we can figure out where it is under the surface. And this circle roughly corresponds to its location. It might be a little too big. I'm not exactly sure about that. That was a little harder to find. And if we look at a core that accumulated on the seafloor actually quite a large distance away, we still see pretty graphic evidence that something very profound happened at this point in Earth history. In particular, what we see in these cores is very fine-grained material like you might expect to be deposited pretty far offshore. Okay, and this is actually a little ridge that juts out in the continental slope. So it's actually not something that turbidity currents and the debris flows flow down very easily. They'll kind of go away from it because it's a high point. It's a high ridge. So very fine-grained sediments. And then right on top of it, we have this coarse-grained deposit, including what appear to be tektites, altered tektites. And a tektite, here's a picture just pulled off of Wikimedia of a couple of tektites from Australia, I think in this case. And they kind of have these funny droplet or barbelly shapes, and they're often pitted and dark on the surface. The idea is that these are essentially bits of glassy material, molten material that was heated up really hot. They're actually among the driest rocks we know of. So they were heated so hot all the water came off probably, and shot through the atmosphere and landed in many cases hundreds of kilometers away from where they were formed, or at least to the extent we can trace back to where the original impact was that created them. And in this case, altered tektites are found here, having been vaulted over the state of Florida. Okay, a long, long way. And so there's a layer of these things suggesting that there was an impact. There was molten stuff falling out of the sky, and then there are some other spherulitic and such layers. There's actually charcoal or carbonaceous deposits. And then finally above that, we start to get kind of a recovery of the system. So something very energetic happened in this location where previously and afterwards it was a very low energy environment. So something very sudden happened and correlates in time very well with the impact in the Yucatan. There are actually other things to tie those things together. And one of these cores, I think the one in the middle, is actually a fairly famous picture of the KT boundary, but usually it is seen in color, and I couldn't find a good color version to show you. So I apologize for that. Okay, so that's an extreme example of cosmogenous sediment. Much more run-of-the-mill cosmogenic sedimentary processes. We have these cosmic dust or interplanetary dust particles that are actually raining into our atmosphere pretty much all the time. Okay, we have little meteorites and things like that come in whenever there's a meteor shower, for instance. And this kind of rains down through the ocean at a slow rate, more or less all the time, and accumulates very slowly on the seafloor. So in addition to these really big violent deposits, we do have a more or less consistent rainout that can actually tell us something about accumulation rates of other types of sediments. So in general, we can rank sediments according to how quickly they're typically deposited, particularly near continental margins. So as we saw, the biggest piles of sediments, mostly terrigenous sediment, accumulate near continental margins. Sedimentation rates there tend to be much higher because that's where most of the sediment is coming in and being deposited, where rivers meet the ocean. So These rates vary a lot, but a ballpark number to keep in mind might be something like 50 meters per million years or a fraction of a millimeter per year. When you get into the deep sea, rates are generally much slower, and we observe this in the map of sediment thicknesses. Once you got away from the continent, sediment was generally much thinner on the seafloor than it was near the margins themselves. And it actually declines as you go from calcareous to silicious to clay to finally manganese nodules, which accumulate excruciatingly slowly where they occur, millionths of a meter per year or less. And so in general, what you should expect to see is in those parts of the ocean where calcareous biogenous sediments survive to the seafloor, where it's relatively shallow in the ocean, you're above the CCD, sediments are going to be dominated by that as long as there's nutrients and as long as it's not all being diluted by terrigenous sediments. And it's really only in areas where calcareous sediments aren't surviving because they're dissolving that you can find siliceous sediments, which generally accumulate more slowly. So you're only going to find a sediment that consists mostly of them if for some reason calcareous sediments aren't being deposited there because they're dissolving. And then finally clay, abyssal clay, this windblown stuff, accumulates the slowest of all. So you're really only going to find sediments that are rich in that stuff if nothing else is happening to first order. And then finally, if you're in a part of the seafloor that's well removed from places like deserts where you can get dust storms and loft abyssal clay into the atmosphere and transport it out in the ocean, you can get accumulations of things like manganese nodules. Okay, so the big picture here is if you're near a continent, you're usually going to be in an environment where terrigenous sediments dominate. Okay, and if you pick up a pile of dirt, sure, you might find some calcareous debris, you might find some diatoms, some siliceous organisms, but most of the sediment you're going to find there is material that's been eroded off the continents, or if you're on an oceanic island, material that's been eroded off of that island. Okay. Once you get away from continents, if you're in a region with high biological productivity and it's relatively shallow above the CCD, typically sediments are going to be dominated by calcareous oozes, okay, debris from calcareous organisms. In deep parts of the ocean or in the Pacific, which is more rich in CO2 and therefore more, boy, I spelled that wrong, sorry, and therefore more acidic and more prone to dissolve calcium carbonate, you'll be more likely to find siliceous oozes, which don't really care about the acidity of the ocean that much, and therefore can accumulate even below the CCD. And then finally, if you're in a low biological productivity environment and you are far away from sources of normal terrigenous sedimentation, perhaps the only thing that will be able to accumulate will be these wind-blown clays. And so we can actually, if we go to a part of the deep sea floor and drill a hole and sample what's there, we can actually make some inferences, for instance, about what did the biological productivity in this place used to be like. Right? If we see lots of siliceous ooze or rocks that were formed from siliceous ooze over time, that might give us some inference that this used to be an area that had a lot of productivity. If we find calcareous sediments, that might give us some inference that this area used to be above the calcite compensation depth, and so on and so forth. Okay, so you're going to actually work with this in more detail in your lab. I'll just give you a preview now, but to put this together, we could imagine tying together this idea of sort of a ranking of the likelihood of finding different types of sediment on the seafloor, combining that with what we know about plate tectonics, in particular the formation of new oceanic crust and lithosphere at mid-ocean ridges and its gradual aging away from those ridges. Okay, so we can imagine we have a divergent boundary where we have two plates pulling apart. So we have our mid-ocean ridge. I've kind of exaggerated the size of the little furrow at the top of the ridge here just so it's easy to see. The summit of these ridges typically is something like 2.5 kilometers below sea level. Okay. Anybody remember what the typical depth of CCD is? It varies from place to place, but there's a ballpark number. All right. Ballpark 4.5 kilometers, 4 or 5 kilometers, something like that. So the peaks of the mid-ocean ridges in most parts of the ocean stick well up above the CCD, which means that carbonaceous sediments, calcareous sediments, don't dissolve before they accumulate on the seafloor. So if they're forming, they can actually accumulate and make a calcareous ooze, okay, near mid-ocean ridges. And that's what we saw when we looked at a picture, for instance, of the oceans and the percentage of calcium carbonate in sediments along the mid-Atlantic ridge and along the East Pacific rise. Those were regions where there are high concentrations of sediment at the surface of the seafloor. Eventually, however, the oceanic crust and the lithosphere underneath it, they're aging. The lithosphere is getting thicker and colder, and so by isostasy, it starts to sink. Okay, the seafloor is getting deeper and deeper. And eventually, it may pass through the CCD. Okay? At that point, calcareous sediments can no longer accumulate. Okay? They're perhaps falling through the water column and landing on the surface of the sediment, but the water is so acidic that they're actually dissolving before another thing can fall on top of them and make a layer. And so what tends to happen once these calcareous sediments get below the CCD is they don't necessarily disappear. It's difficult for the acidic water to get down into these very fine-grained biogenous sediments and actually eat them in place. So they tend to stay there. There can be some dissolution and stuff that happens, but whatever's accumulated above the CCD tends to stay in place and in turn gets buried by other materials once it gets deeper. And if you're in a region of the ocean, let's say near the equator, okay, where for one reason or another there is lots of nutrients in the surface water, you might have lots of biological activity, and siliceous organisms fall on top of that and accumulate as a siliceous ooze layer, okay, even below the CCD. If you're in a region of the ocean for whatever reason that doesn't have very many nutrients in the surface waters or isn't very biologically productive, the only thing that's really left to accumulate might be abyssal clay or manganese nodules, depending on where you are in the ocean. Okay, and of course, this stuff accumulates very slowly, so you might not expect there to be very much thickness of it. And if you're in a part of the ocean that's not very productive, even the calcareous layer may not be very thick. Okay, so low biological productivity, we might just generally see less sediment in total. High biological productivity region, we might see a thicker pile of sediments. And of course, if we were to drill a hole over here through this sediment, we would find on the top of our drill core a layer of siliceous ooze. Beneath that, a layer of calcareous ooze, perhaps some sediments associated with the volcanic activity here. There's some special sediments that occur like that. And then eventually down into basaltic rock, typical oceanic crust, from which we can infer that this had been in a high biological productivity region. We can even figure out how long ago it passed through that CCD, so we could back out where the CCD used to be in the ocean, for instance, at some point in the past. Likewise, a drill core over here would intersect abyssal clays for a while and then a thin layer of calcareous ooze before it hit basalt, from which we might infer that this is a low productivity part of the ocean and has been for some time in the past. Does that make sense? So in this case, drilling down is actually taking us back in time, which is generally true when we look at sediments. If we look at a map view, simplified, okay, we can see what's happening now if we look at the sediments accumulating at the surface of the seafloor. And the coloring here is not very obvious, but these lightish colors are mostly calcareous oozes. The white color is mostly terrigenous sediments along continental margins. And then the various greenish colors are siliceous oozes of one kind or another. And then this pink color is abyssal clay for the most part. And H's mean that they're hydrogenous sediments, which mostly means manganese nodules. Okay, and so what we can see is along the mid-ocean ridges, okay, where the oceanic crust is relatively young, along the East Pacific rise, along the ridge in the Indian Ocean, more or less, you see calcareous oozes. You're pretty far away from the continents, not strong sources of terrigenous sediments. You're above the CCD, so calcareous oozes accumulate. And then once the seafloor gets older and deeper, it falls below the CCD, and particularly once you get in the North Pacific, which has the most CO2 in it, and the CCD is the shallowest, there you see mostly either siliceous oozes or abyssal clays. And in fact, in most places you see abyssal clays, the siliceous oozes are concentrated in this belt around Antarctica, right along the equator, and again near the North Pole. And this idea that the presence of siliceous ooze is an indicator of biological productivity in the surface ocean, from that you can infer perhaps there's lots of productivity here Lots of productivity here, lots of productivity here. The question then is why? Why is the ocean not uniformly productive? Why is productivity enhanced near the poles and near the equator and not so high in between? That's going to be one of the major questions we're going to be asking when we start talking about how winds blow across the surface of the ocean and how the ocean responds by flowing itself. Okay, any questions about that? Okay, so a fair question to ask is, I've talked about drilling in the ocean. How do we know what's on the seafloor? Here's a picture of the latest and greatest. This is the research vessel Chikyu, I'm sure I'm mispronouncing that, which is actually Japanese, but participates in international drilling programs. And I actually showed you in the last lecture a picture of some of the first drill cores that this ship recovered. It's the latest and greatest because it can go to fairly deep ocean water and it can drill pretty deep cores. Okay, and you can see that's sort of like a floating oil rig, right? Here's a big drilling derrick. It's a pretty big ship overall, and it can maneuver itself very nicely. Okay, and there actually have been a succession of these. There's the JOIDES Resolution, which did a lot of drilling work going back for quite a while. So we actually have dedicated ocean drilling vessels whose purpose in life is to go around to various parts of the Earth's ocean, drill cores into the sediments, and in some cases into the crust underneath them, so that we can infer things about what that oceanic environment was like going back in time. Okay, and in fact, there's a program, you can write a proposal and say, I think you guys should go here and drill a hole. Okay, and here's why you should drill a hole, because we'll learn something about a mass extinction, or we'll learn something about flow in the Santa Barbara Channel, whether or not Santa Barbara Channel has always been oxygenated or sometimes runs out of oxygen, for instance. All right. So for the rest of the lecture today, we'll start talking about properties of seawater. And this will be, the properties of seawater will be the last topic that you'll be responsible for the midterm. Okay, so we're going to talk about physical properties of seawater and chemical properties of seawater. We're going to start out with a little bit of chemistry, because otherwise some of the physical properties of water won't make as much sense. At least that's the hope, that it'll make more sense. So this probably is a review for most of you, but nonetheless we'll go through. Just to remind you that an atom is sort of the fundamental building block in chemistry. So an atom is something that's the smallest thing that you can get to by doing chemical reactions, heating things up, cooling them down, burning them, crystallizing them, so forth. Okay, and an atom consists of two basic parts. There's a nucleus, which is where most of the mass of the atom is. That nucleus consists of positively charged particles, protons, and most nuclei also contain these neutral particles, neutrons. In this case, helium always has two protons. That's the definition of helium. It's an atom with two protons in it, two positive charges. Most helium atoms have two neutrons, two neutral charges. There are a few helium atoms, some fraction of them, that actually only have one neutron in them. They're perfectly happy. They're just rarer. The number of neutral particles in the nucleus can actually vary without changing the name of the element. And then that positively charged massive part of the atom is surrounded by really a cloud of electrons. Here it's shown as like an orbit, but it's actually some smeared out probability distribution of electrons. These contain the negative charge. They're basically responsible for chemistry. So bonds are formed essentially by the interaction of electrons with each other. Okay, but they contain relatively little of the mass of the atom. Now in this case, I've shown you a picture of helium. Helium usually exists in the natural environment as just lone atoms. It doesn't really form chemical bonds very easily. And so usually what you see when you see a helium atom will be something with two charges in the nucleus and two charges floating around as the electrons outside it, giving you a neutral atom, okay, a lone atom. That's not always true, and in fact, the most interesting things don't always occur that way. You can have atoms that have a different number of electrons than protons, so they have a net charge, either positive or negative. Okay, and in fact, there are two types. There are ions that have extra electrons and therefore have a net negative charge. Okay, and we call those anions. A good example would be chloride. There are ions that have too few electrons. They've lost some electrons and therefore have an extra positive charge. Okay, and we call those cations. The useful mnemonic is that cation has a little plus in it, right? If you think of the T as being a plus. So that might help you remember. So, for example, sodium, which is a common cation, particularly dissolved in ocean water. It's the most common cation in ocean water. Sodium always has a charge of 11 in its nucleus. Most commonly, however, when you find sodium in nature, it will only have 10 electrons bound to it. So it has a net charge of +1 because it's usually missing an electron. Okay, it's happiest that way. And this is, in fact, common. Elements on the left side of the periodic table tend to lose electrons and become positively charged. Elements on the right side of the periodic table tend to take up extra electrons and become negatively charged. And of course, we can not just have atoms have a net positive or negative charge, but we can actually bond them together and make complex molecules that contain more than one atom bound together in some way. Okay, so let's look at that in a little more detail. Here's the periodic table again. Okay, just listing the elements according to several chemical properties, but in particular, the ordering from left to right and then down the rows is in terms of numbers of protons in the nucleus. So hydrogen has 1 proton in the nucleus. Helium, which I showed you a picture of, always has 2 protons in the nucleus. It can have 1 or 2 neutrons. Lithium has 3, beryllium has 4, boron 5, 6, 7, 8, 9. In fact, that's what that number indicates, is how many positive charges are in the nucleus. And what I just told you when we talked about ions is that these guys, the ones that are outlined in the pinkish color here, on the left side of the periodic table, and really most elements in the world, in the natural environment, will tend overall to give off electrons. They tend to get rid of their electrons and become positively charged. They become cations. Okay, so sodium, I showed you a picture of that, typically is positively charged. It has 1 positive charge. It's lost 1 electron. Potassium and lithium, in fact, all the elements in that column tend to be +1 charged. This column tends to be +2. This column tends to be +3, but not very soluble in seawater, so you don't really have to worry about it, and so on and so forth. All of these guys tend to be positively charged in seawater, or even when they form rocks on land. And in the right side of the periodic table, particularly oxygen, fluorine, chlorine, bromine, iodine, tend to form anions. They tend to grab extra electrons and become negatively charged. Okay? The only elements that we really commonly find in nature without having a charge associated with them is this one column here, which includes helium at the top, called the rare gases or the noble gases. Okay? For the most part, elements actually don't like to be neutral. They're much happier either bonded to something else or losing some electrons or picking up some extra electrons, which is what makes chemistry interesting. It's not the study of lone atoms. It's actually the study of interactions between atoms that are trying to share or grab or give up electrons. And so the story of bonding is actually going to be really interesting for figuring out why water behaves the way it does, why seawater isn't just pure water. And so we can think of atoms interacting with each other to make molecules, and it turns out that they can do this in several different ways, or at least it's convenient to divide the ways they do it into several different explanations that usually are hybridized in some way. So we can think of covalent bonds where 2 atoms will share electrons in some way so that each of them can have the number it really wants, okay, which usually means to have the same number of electrons as the nearest element in this right-hand column of the periodic table, the noble gases. Okay? So hydrogen, which has 1 positive charge in its nucleus and usually has 1 electron if it's in the form of an atom, it wants to be like usually either helium or it wants to have no electrons at all. And so if it gets near something like oxygen, which has 8 positive charges and 8 negative charges in its atomic form, it will try to grab onto one of those electrons and share it so it has a helium-like structure. Okay? And oxygen, it wants to have a neon-like structure. It wants to grab a couple of extra electrons and become like neon, like its nearest noble gas neighbor. And so it says, okay, you can borrow one of my electrons as long as I can borrow yours. and then it tries to do that from another hydrogen atom, and then it goes from 8 to 9 to 10. Okay? So here we have hydrogen sharing its electron with oxygen, oxygen sharing its electrons with 2 hydrogen atoms, both of them ending up happier, chemically speaking, and that sharing of electrons binds the atoms together to make a molecule. So instead of 1 oxygen atom and 2 hydrogen atoms, now we have one water molecule. So that's electron sharing covalent bonding. That's not the only way to make atoms stick together. We can also have ions of opposite charge associate with each other. So sodium usually likes to give up an electron and become positively charged. Chlorine usually likes to grab an extra electron and become negatively charged. They're actually happy to do that even if there aren't other atoms for them to bond to or share with. However, opposite charges attract each other. So the positive charge of a sodium will tend to attract any negative charges that are sitting around, and so they'll tend to associate with each other just because they're ions of opposite charge. So we call that ionic bonds. And then finally, the weakest of all, at least for the purposes of this class, is hydrogen bonding. Okay? And we can rationalize hydrogen bonding actually by thinking about how water molecules are held together. And I'll get to that in the next slide, but I just want to mention that here so that we can kind of rank these guys in terms of their strength. Usually we think of covalent bonds as being the strongest. Ionic bonds can be quite strong, and hydrogen bonds are the weakest. Okay, so the bonds that hold an individual molecule together turn out to be fairly strong. Bonds that associate molecules with each other tend to be weaker. Okay, so let's look in more detail at how water is held together. So we have an oxygen atom. We have 2 hydrogen atoms. They agree to share electrons so that each of them is happier. And we make this Mickey Mouse head shaped thing a water molecule. Okay? And you can kind of actually rationalize why it looks a little bit like Mickey Mouse's head. We have a pair of electrons here. We have a pair of electrons here. We have 4 other electrons, and they're like charge, right? Electrons have the same negative charge. In general, they don't like to hang out together. They'll try to move away from other electrons when they can. So these electrons are going to try to move away from these electrons, and they're all going to try to move away from these electrons and these electrons. So we have kind of this big oxygen atom, and we have 4 pairs of electrons arranged around it, trying to get as far from each other as possible around that oxygen. Okay, so we have a sphere with 4 points that are trying to get as far apart as possible. That actually makes a tetrahedron, okay, a shape with 4 corners. But 2 of those corners are just electrons, and the other 2 corners are hydrogen atoms. And so they kind of go towards the corners on one side of that oxygen and make these 2 ears with an angle of something like 105 degrees. Not quite a right angle, a little bit bigger than that. And it turns out the angles between the corners of a tetrahedron are 109 degrees. So it's pretty close to that angle. Okay? So we can actually draw a picture of this like this, where we show the oxygen in red and the hydrogen in white and the bond in between them with a little stick. Okay? This is a ball and stick diagram showing the basic shape of oxygen. And we can think about how hydrogen bonding might work by looking at this picture. Okay? This is obviously a simplification, but here we have this positive charge for the hydrogen atom. Okay? And it's sharing its electrons with the oxygen. So if we just think about where the charges are distributed in this picture, we have the positive charge out here, and the negative charges are tending to hang out along the line between the hydrogen atom and the oxygen atom. So they're actually closer in. The positive kind of sticks out. The negatives are kind of pulled in. Okay? Same up here. Positives kind of sticking out, the negatives being pulled in. So overall, what we should expect to see is this is a covalent bond, but there's a little bit of kind of extra positive charge out here because the nucleus is sort of hanging out on the outside a little bit more than the electrons are. So there's a net positive charge here, and there's a net positive charge here. It's not a full electronic charge, but some fraction of one. Okay, and of course, this is a neutral molecule, so if there's extra positive stuff here and extra positive stuff here, the implication is there must be some extra negative stuff on this side somewhere to make it neutral. Okay, so we have a slight positive charge, a slight positive charge, and a slight negative charge. And opposite charges attract. So you might think, aha, this positive charge for one molecule might be attracted to the negative charge on the next door molecule. And so we might think of water molecules as kind of tending to stick the Mickey Mouse ear of one molecule to Mickey Mouse's face of another molecule, okay, and so on and so forth. So we make a network of ear-to-face connections. Okay, and this is basically what hydrogen bonding consists of. So we can think of each water molecule, okay, as having two hydrogen atoms that each of which with a slight positive charge that will tend to attract the negatively charged oxygen of a different water molecule. Okay, and each oxygen, because the oxygen atom is actually quite big, is capable of actually attracting a couple of hydrogen atoms from other adjacent water molecules. And so the molecule itself is held together by these strong polar covalent bonds. Between molecules, there are these weaker interactions of the slightly positively charged hydrogens with slightly negatively charged oxygens of other water molecules. Okay, so individual water molecules will tend to stick together unless something is pulling them apart, or unless they have just too much energy to associate with each other because they're flying around at high speed. And this is actually what a hydrogen bond is. Okay? It's this tendency for hydrogen in one molecule to attract oxygens from a different molecule. This doesn't just happen for water, but it is a prominent property of water. And this property tends to make water molecules stick together. Water is a sticky molecule. Okay? I actually do some work with vacuum, where we want to pump all the gas and molecules out of a volume so that we can do things under very controlled conditions. And water is really bad news in these systems because water just tends to stick to stuff. It doesn't want to go into the vacuum pump. It tends to stick to the walls of the container, or it'll stick to itself. And so it's badly behaved in these systems. So we can come up against the stickiness in the lab. And of course, you can come up against the stickiness just when you turn on the tap and liquid water comes out, because that turns out to be what holds liquid water together as this hydrogen bonding property. Okay. Turns out also to have implications for oceanography, because this also leads to the solvent power of water. Water is very good at dissolving things. It's particularly good at dissolving things that have also the ability to form hydrogen bonds, or it's also good at dissolving things that tend to form ions. Okay? You can imagine if I have a sodium ion that's got a positive charge, these negatively charged oxygen ends of water molecules are going to tend to stick to it and bring it up into solution. Okay? And this tendency to form lots of hydrogen bonds contributes to some really strange thermal and density properties of water. Okay. One of those thermal properties is heat capacity. Every time one water molecule and another water molecule interact this way, okay, they're coming together, attracted by their opposite charges. Okay, so they're energetically drawn together. And when that happens, there's some energy stored in that bond. If you want to break it again, you have to put energy into it to pull them apart. Okay, so when you form a bond, you give off some energy, and in order to break a bond, you actually have to put energy into it, okay, to get rid of that, to break that bond apart. And so in a substance capable of making hydrogen bonds, like water, the process of breaking and forming these bonds can accumulate or distribute heat. Okay? Every time you make a bond, you give off a little heat. Every time you break a bond, you absorb a little heat. There are lots of these hydrogen bonds in liquid water, so you can imagine that water has a great capacity to store heat in the form of creating or destroying hydrogen bonds. And this turns out to be really a remarkable property of water, particularly liquid water, that it has a very high capacity to store heat. You have to take and put a lot of heat into water to change its temperature very much. Because mostly what happens when you add energy to water is that you break some hydrogen bonds. And if you try to cool water down, instead of changing the temperature very much, mostly what you do is make new hydrogen bonds. Okay? So it takes a lot of heat to change the temperature of water, the converse of which is, if you have a big pile of water, you can get a lot of heat out of it without changing its temperature very much. Okay? And so if we quantify heat capacity in terms of the amount of heat, calories, stored per gram, which is about 1 cubic centimeter of water, how much heat do you have to add or subtract from water to change its temperature by 1 degree Celsius? In the case of liquid water, that number is 1. That's actually the definition of a calorie. Most substances, like rock, are much lower in their heat capacity. If you add the same amount of heat to a rock, its temperature will go up a lot relative to water. Even other liquids, for the most part, like gasoline, have lower heat capacities than water does. Okay? Metals, like your iron frying pan or like the Earth's core, have very low heat capacities. The only substance really that you're likely to ever come across that has a higher heat capacity than water is ammonia. And actually, ammonia is a very close cousin of water. Okay? Water is oxygen with 2 hydrogens. Ammonia is a nitrogen atom with 3 hydrogens. And it can also participate in the formation of hydrogen bonds. So it's actually another example of the same kind of story. Okay? High heat capacity is associated with the formation and destruction of hydrogen bonds. Okay? And this is really useful for us because it means that water is a great medium for moving heat around. Okay? So the reason why radiators, okay, are powered by either hot water or steam is because water has a great capacity to move heat around without changing its temperature very much. And this isn't true just for heating up a house. It's also true for the natural world. And we can see the ocean essentially acting as our radiator. It acts as a moderating agent on our climate because it can store so much heat without changing its temperature very much. So we live in Los Angeles. We live in coastal Los Angeles. If we look at one of the nearby weather stations at LAX, the airport is actually right on the beach, just about. And so most of the time, the wind is actually blowing off the ocean. And the ocean has this tremendous capacity to store and give off heat without changing its temperature very much. So the winds that are blowing off the ocean pretty much are always the same temperature all year round. As a result, the climate in West LA is wonderful. The temperature is nice pretty much all year. Okay, it gets a little bit warmer in late summer. It gets a little bit cooler in late winter. But the variation from one time of the year to one part of the year to another, the seasons in Los Angeles are really moderate. Okay, and that's essentially a reflection of the fact that the ocean is heating up and cooling down. It's absorbing and redistributing this heat without changing its temperature very much, even though the sunshine is getting more and less intense or is shining longer each day during the summer. If we go to a part of our continent that doesn't have this influence of the high heat capacity of water, like Omaha, Nebraska, which kind of sits right in the middle of the United States, okay, the difference between summer and winter is much greater. Omaha has a kind of continental climate, born of the fact that it's not near ocean, gets influence from the Gulf of Mexico, particularly during the rainy part of the year, but not nearly as much as Los Angeles does, and so its climate actually goes up and down a lot more. It's not being buffered out by the ocean storing and releasing energy during different seasons of the year. So our nice weather is actually pretty much a reflection of the high heat capacity of water and the fact that we live close to a big body of water. Okay, this is where I show how old I am. Another example of sort of sensible differences in heat capacity is from an old style chicken pot pie. I know they don't make them this way anymore, but I like this example, so I'm going to tell it to you anyway, even though you're going to think I'm a fogey now. Okay, so it used to be, if you went to the grocery store when I was in college and we were poor and starving, and you had like 50 cents to get dinner, you could get like a pot pie because they were always on sale. And they came in this little foil pie pan, okay, and you stuck it in the oven for 45 minutes or whatever. We didn't really even have a microwave. And after 45 minutes or so, it would be done, usually. Sometimes it was still frozen in the middle, but assuming that didn't happen. And you would, of course, go to pull it out of the oven. And what quickly you discovered is that if you were really careful, you could actually just grab the foil and pull it out of the oven and put it on the top of the stove without burning yourself. Okay? Now this is something that's been sitting in the oven for like 45 minutes. So it's actually hot. Okay? The foil's probably at about the same temperature as the oven, or it's at least the temperature of the filling of the pie, which is basically water. Okay? It's water with some salt and chicken and peas or whatever the pie is made out of. So 100 degrees Celsius. Okay, that's plenty hot to burn you. But the heat capacity of the aluminum foil is so low, partly because it's thin and mainly because it's metal, that when you grab it with your fingers, the heat capacity of your fingers is so much higher that the whole thing cools down without burning your fingers very much. Okay, the temperature of your finger doesn't change very much. The temperature of the aluminum foil comes down to close to your body temperature. Okay, but if you stick your finger inside the pie, you're in for a world of hurt. Because the heat capacity of the pie, being mostly water, is the same as the heat capacity of your finger, which is also mostly water. And so the thing kind of comes to an equilibrium near the boiling temperature of water, which hurts. So aluminum foil out of the oven, if you're careful, okay. Although, don't sue me if you get a burn doing this. Do not grab the pie itself when you pull it out of the oven. That is a bad idea. Perhaps a similar concept that you've actually had some experience with is if you go to the beach on a really hot summer day, sunny summer day, okay, the sand might actually be kind of hot to the touch. Okay? It heats up really quickly when the sun is shining on it. It has a low thermal inertia, which is to say, has low heat capacity because it's made out of rock. And also the heat doesn't penetrate very far into it because it has a low thermal conductivity. And so it gets hot during the day and it actually gets cold very quickly at night. Okay? But of course, you run across the sand and you jump into the water, and the water is the same temperature in the day as it is at night. Heat capacity is so much higher, its thermal inertia is higher, it doesn't even really care if the sun is up or not. Okay? It heats up a tiny little bit during the day and it cools down a tiny little bit at night, but not enough that you could really notice. So water, very high heat capacity. Pretty much everything else, much lower heat capacity. Now, all the heat capacities I've been talking about are described in terms of changing of temperature, right? So changing the temperature of the foil when you grab it. Changing the temperature of the air when it flows across the ocean during the summer or the winter to get to LAX. Okay, so those are examples of heat being transferred as the temperature of something is changing. Okay, and you can think of that as being heat that you can sense, right? The temperature is changing, so I know somehow heat is being added or subtracted. That's not the only way that heat gets around, however. Okay? Another way that heat can move is to change the state of matter. In particular, if you go from solid to liquid or from liquid to a gas, the three main states of matter, at least relevant to oceanography, there's plasma, but there's not a lot of plasma in the ocean, so we're not going to worry about that for this class. It actually takes energy to do those processes, to boil water, to melt ice. Okay? And so here's just a time-lapse picture of some ice melting. Okay, this is an example of just a glass of ice sitting in the room. It's absorbing heat from the room, and that heat, in this case, is actually going towards the conversion of solid water to liquid water. And here we have, this really isn't relevant to oceanography, but I think it's just cool. This is a NASA movie where we have just water boiling because we have a hot filament. And this is the same process going on the space shuttle where there's no gravity. Okay, so instead of actually boiling and the water rising to the surface, here we just make a big bubble of steam and it just kind of sits there. Okay, so this is what actually happens if you allow convection to happen. So the steam plus water is actually much less dense and it's hotter. So it rises and is replaced by cold water that then boils and makes a circulation. In this case, there's no gravity, so the steam just sits there and can't move, and the heat can't be distributed as efficiently. Okay. So heat capacity. How does this relate to phase? Well, think of liquid water. In liquid water, we have these water molecules, right? And they're packed together. They're stuck together by hydrogen bonds. But they aren't completely hydrogen bonded together. It's liquid. They're not trapped in place. It's deformable. And so what happens if you take the liquid and you add some heat to it? Well, you're going to break some of those hydrogen bonds. Okay, in addition, some of that heat's going to go to make the molecules move around just faster, which is what we sense as temperature. And if you cool that liquid water down, you're going to make some new hydrogen bonds. Okay? So liquid water, by forming new bonds or by losing old ones, has a great capacity to accept or give off heat without changing its temperature very much because of that capacity to create or destroy new hydrogen bonds. If we go to a solid, we can think of that as being the extreme hydrogen bonding limit. All of the water molecules are essentially stuck to as many other water molecules as they can be. So each hydrogen, in addition to being attached to its own water molecule, is stuck to the oxygen of another water molecule. And each oxygen in a water molecule is forming two hydrogen bonds with other hydrogens from other molecules. So if you take ice and you warm it up, as long as it's still ice, all those hydrogen bonds are still there. And if you cool it down, it's already basically completely hydrogen bonded. You're not making any new hydrogen bonds. Okay? So its capacity to accept or give off heat by forming or destroying hydrogen bonds is much less than liquid water. So its temperature actually changes faster when you add or subtract heat from it, because that heat is not going to create or destroy hydrogen bonds like it is in liquid water. Okay, it's just going to make the things vibrate faster, which is what we sense as temperature. Likewise, if we go to vapor, okay, here we just have water molecules flying around more or less free. Okay? And if we cool it down or warm it up, as long as it's still vapor, they're more or less just flying around and bouncing off of each other. We're not really forming or destroying any hydrogen bonds because there really aren't any hydrogen bonds there. Okay? So we should expect from that kind of argument, and I am simplifying, however, that liquid, because it can create and destroy hydrogen bonds within the same phase, should have the highest capacity to store heat. And in fact, that's what we observe. Its heat capacity is roughly twice as high as either ice or steam. So if you take the same amount of heat and you add it to ice, its temperature will change twice as much as if you added that amount of heat to the same mass of liquid water. And steam will also change its temperature relatively quickly with relatively little addition of heat. Okay? In addition, as I just mentioned, it takes energy to go from one phase to another one. So let's think of starting out with some really cold ice at minus 30 degrees Celsius, which is minus 22 degrees Fahrenheit. And we start adding heat to it. Let's say we have some ice and we just plop it down on a stove, okay, and we turn up the burner. As the burner goes, we're adding energy to the ice, and as long as it stays ice, its temperature starts to increase. Okay? For every calorie we add to a gram of ice, its temperature will go up by a couple of degrees Celsius. A calorie is about 2 joules. Sorry for the x-axis here, it was just easier to make it this way. And so its temperature is going up as we're adding heat to it until it gets to 0 degrees C, at which point, what happens to the ice? It starts melting. Ice melts at 0 degrees Celsius. And what we'll see is that, in fact, the temperature will sit at 0 degrees Celsius as long as there's ice present while it's on the burner. And the energy from the burner is still going into that sample of ice, okay? But instead of increasing its temperature, that energy is instead converting ice into liquid water, okay, by breaking up a bunch of those hydrogen bonds. Okay? And it's going to stay at 0 degrees Celsius until you've broken up all those ice crystals and released them into the liquid. Only then will the temperature start to go up again. The heat capacity of liquid water is higher than the heat capacity of ice, so this line doesn't slope quite as steeply as the ice line. As we add energy to liquid water, its temperature goes up to 100 degrees Celsius, at which point it starts to boil. Okay, and then the temperature stops moving again, because now we're breaking all of the leftover hydrogen bonds and liberating that water into steam. And that takes a lot of energy, okay? But it all takes place at one temperature. Then once all the liquid is gone, we're left with steam, and the temperature starts to go up again. So when we come back on Monday, we'll go over this again in a little bit more detail and talk about what kind of heat is being added in each stage of that process.